In the spring of 1943, the Allied bomber crews flying over occupied Europe faced an impossible challenge. The Third Reich had transformed the continent into a fortress with massive concrete structures that seemed indestructible. Bridges, submarine pens, viaducts, and bunkers built with reinforced concrete walls, 10, 15, sometimes 20 feet thick. Conventional bombs bounced off them like pebbles thrown against a castle wall. The Allies dropped thousands of tons of explosives, and yet these structures stood defiant, mocking every attempt to bring them down. But then something changed, something that would make German engineers question the laws of physics itself. Before we dive deeper into this incredible story, if you're fascinated by the untold engineering marvels and secret weapons of World War II, make sure to hit that like button and subscribe to the channel. We bring you the most compelling stories from the war that you won't find anywhere else. And don't forget to leave a comment telling us what other World War II mysteries you'd like us to explore. The year was 1940, and Britain stood alone against the Nazi war machine. The Luftwaffe had failed to break the Royal Air Force during the Battle of Britain, and Hitler's planned invasion had been postponed indefinitely. But the threat was far from over. German U-boats prowled the Atlantic in wolf packs, strangling Britain's supply lines. These submarines operated from massive concrete pens along the French coast, structures so heavily fortified that they could withstand direct hits from the largest bombs in the Allied arsenal. The RAF tried everything. They dropped blockbusters, incendiaries, even experimental weapons. Nothing worked. The concrete roofs of these U-boat pens were up to 16 feet thick, reinforced with steel, and designed by some of Germany's best engineers. In the offices of Vickers Aviation in Weybridge, England, a brilliant but unconventional engineer named Barnes Wallis was wrestling with this exact problem. Wallis was already famous in aviation circles. He had designed the geodetic airframe that made the Wellington bomber one of the most successful aircraft of the early war years. But Wallis wasn't satisfied with conventional thinking. He had a reputation for asking questions that others considered impossible. What if, he wondered, the problem wasn't the size of the bomb, but how it was being used? Traditional bombing doctrine of the era was simple. Drop as many explosives as possible, directly on the target, and hope for the best. But Wallis understood physics in a way that most military planners did not. He realized that concrete, despite its strength, had a critical weakness. It was incredibly strong under compression, but relatively weak under tension and shear forces. A bomb exploding on the surface of concrete would dissipate most of its energy outward, into the air. But what if you could get the bomb to penetrate deep into the ground, next to the structure, and then detonate? The explosion would create a seismic shock wave, a camouflage effect, that would shake the very foundations of the structure apart from below. This wasn't just theory. Wallis had studied earthquake mechanics, mining engineering, and even medieval siege warfare. He understood that castles fell not because their walls were battered down from the outside, but because sappers tunneled underneath and collapsed them from within. He wanted to create an artificial earthquake, a bomb that would burrow deep into the earth and unleash its fury where the target was most vulnerable. The concept was revolutionary, but it came with enormous technical challenges. To penetrate deep enough, the bomb would need to be extremely heavy and moving at tremendous speed when it hit the ground. It would need a specially hardened casing to survive the impact without shattering, and it would need to be dropped from a very high altitude to achieve the necessary velocity. This meant developing not just a new weapon, but an entirely new way of bombing. Wallis began his calculations in 1941, working often late into the night, filling notebooks with equations and diagrams. He envisioned a bomb weighing 10,000 pounds, streamlined like a javelin, dropped from 30,000 feet or higher. At that altitude and weight, the bomb would accelerate to supersonic speeds, punching through soil and rock like a needle through fabric. The explosion, occurring deep underground, would create a massive cavity and send shock waves rippling through the earth. Any structure within the shock wave radius would be shaken to pieces, its concrete cracking and crumbling as if struck by an earthquake. But convincing the military establishment was another matter entirely. The RAF was skeptical. They were fighting a desperate war with limited resources, and Wallace was asking them to invest in an unproven concept that required not only a completely new type of bomb, but modifications to their heavy bombers and extensive training for crews. Many officers thought the idea was too risky, too experimental. Some even called it fantasy. But Wallace was persistent, and he had allies who recognized his genius. By 1943, the situation had become critical enough that the Air Ministry was willing to take chances. The Allied bombing campaign was intensifying, but key targets remained frustratingly intact. The Mona and Ader dams in Germany's industrial heartland were high-priority targets, and Wallace had already been working on another revolutionary weapon for that specific mission, the bouncing bomb. That weapon's success in Operation Chastise, the famous Dam Busters raid of May 1943, gave Wallace the credibility he needed. When he proposed his deep penetration bomb, this time, the authorities listened. The weapon that emerged from Wallace's workshop was called Tallboy, and it was unlike anything the world had seen. Weighing 12,000 pounds, it was a sleek, streamlined projectile, 21 feet long, and just 38 inches in diameter. The casing was made of high-grade steel, heat-treated, and specially hardened to withstand the enormous forces of impact. Inside was 5,000 pounds of Torpex, a powerful explosive mixture more devastating than conventional TNT. The bomb's aerodynamic shape gave it remarkable stability and accuracy in flight. It even had offset tail fins that caused it to spin during descent like a rifle bullet, further improving its precision. But creating the bomb was only half the battle. To deliver it effectively, the RAF needed bombers capable of carrying such a heavy load to extreme altitude. The Lancaster bomber, already the workhorse of Bomber Command, was chosen for modification. Special squadrons would be formed, their aircraft stripped of unnecessary equipment, to save weight and fitted with more powerful engines. The bomb bay doors were modified to accommodate Tallboy's unusual size. These would be elite units, flying the most dangerous and important missions of the war. The man chosen to lead this effort was Wing Commander Leonard Cheshire, a decorated pilot who had already completed more than 100 combat missions. Cheshire understood that dropping Tallboy wasn't like conventional bombing. The weapon's effectiveness depended on incredible accuracy. Missing by even a few dozen yards could mean the difference between total destruction and no effect at all. He developed new tactics, flying low over targets in a fast Mosquito aircraft to mark them with flares while the Lancaster bombers circled high above, waiting for the perfect moment to release their precious cargo. The first operational use of Tallboy came on June 8, 1944, just 2 days after D-Day. The target was the Saumur railway tunnel in France, a critical transportation link that the Germans were using to move panzer divisions toward the Normandy beaches. Conventional bombing had failed to collapse the tunnel. Now it was Tallboy's turn. 19 Lancasters from 617 Squadron, the same unit that had carried out the Dam Buster raid, took off carrying the new weapon. They climbed to 18,000 feet and released their bombs in precise sequence. What happened next astonished the intelligence analysts studying reconnaissance photographs. The tunnel hadn't just been damaged, it had been obliterated. One Tallboy had struck the ground near the tunnel entrance and penetrated 60 feet before detonating. The explosion created an enormous crater and sent shock waves through the limestone bedrock. The tunnel roof, thick reinforced concrete designed to survive any conventional attack, simply collapsed. 80,000 tons of rock and debris filled the tunnel. The German panzer division that had been racing to Normandy was stopped dead in its tracks. The reinforcements never arrived, and the Allied beachhead was secured. One bomb in one mission had accomplished what hundreds of conventional raids had failed to achieve. The Germans were baffled. When their engineers examined the damage, they couldn't understand what had happened. There was no impact crater on the tunnel itself, yet it had been destroyed from within. Some German officers reported that the British must have developed some kind of new weapon, something beyond conventional explosives. Rumors spread through the Wehrmacht about supernatural forces, about weapons that defied the known laws of physics. German propaganda tried to downplay the incidents, but the evidence was impossible to ignore. In their reports, some German engineers used words that translated to sorcery and dark arts. They simply couldn't comprehend the science behind what they were witnessing. The success at Saumur was just the beginning. Throughout the summer and fall of 1944, Tallboy proved its worth again and again. The weapon's most spectacular demonstration came against targets that had long been considered invulnerable, the German U-boat pens. These massive structures dotted the French Atlantic coast, concrete fortresses where submarines could be repaired, rearmed, and resupplied in complete safety. The pens at Brest, Lorient, Saint-Nazaire, and Bordeaux had been attacked hundreds of times by Allied bombers with minimal effect. Now, Tallboy was unleashed against them. On August 5, 1944, a force of Lancasters struck the U-boat pens at Brest. The results were devastating. Tallboys didn't attempt to blast through the massive concrete roofs directly. Instead, they buried themselves in the ground around and beneath the structures, detonating deep underground. The resulting shock waves propagated through the rock and concrete foundations, creating cracks and fractures that spread like spider webs. The roofs, no longer supported properly, began to collapse under their own weight. In some cases, entire sections of the pens simply disintegrated, the concrete breaking apart as if it had turned to chalk. German submariners who survived the attacks described scenes of absolute terror. The ground would suddenly heave and shake as if struck by an earthquake. Then, seconds later, the massive concrete roof above would begin to crack with sounds like thunder. Huge sections would fall, crushing submarines and equipment below. The men called it bombardment from hell, an attack that came not from above but from below, from the earth itself. They had no defense against it, no way to strengthen their bunkers further. The concrete that had protected them now became a death trap, crumbling and falling on their heads. By the fall of 1944, the Allied advance across France had liberated most of the submarine pens, but Tallboy's work was far from done. The weapon now turned its attention to targets inside Germany itself. Bridges became a priority. Germany's war machine depended on its transportation network, and the Rhine and its tributaries were crossed by dozens of massive viaducts and bridges, many of them built with such solid construction that conventional bombing was hopeless. These weren't small structures. Some were engineering marvels built in the 19th century with arches of solid stone and reinforced with steel and concrete. They had stood for generations and were expected to stand for generations more. The Bielefeld Viaduct was one such target. This railway bridge in northwestern Germany was a key link in the transportation system supplying the Ruhr industrial region. It was a massive structure with arches made of solid stone masonry, each pillar sunk deep into bedrock. The RAF had attacked it multiple times with conventional bombs, expending thousands of tons of explosives. The bridge remained standing, its structure barely scarred. It became a symbol of German engineering prowess and Allied frustration. On March 14, 1945, 617 Squadron was ordered to destroy the viaduct. This time, they brought not Tallboy, but an even more devastating weapon that Wallace had been developing, the Grand Slam. If Tallboy was impressive, Grand Slam was simply monstrous. Weighing 22,000 pounds, nearly 10 tons, It was the largest bomb used operationally during the entire war. It was 35 feet long and nearly 4 feet in diameter. The bomb was so heavy that only specially modified Lancasters could carry it, and even then, they could carry nothing else. Everything non-essential was stripped from the aircraft. Armor plating, guns, even the bomb bay doors were removed. Grand Slam worked on the same principle as Tallboy, but everything was scaled up. Dropped from even higher altitude, it would reach speeds approaching supersonic, penetrating 100 feet or more into the earth before detonating its 9,000 pounds of explosive. The seismic effect would be catastrophic to any structure within hundreds of yards. When the first Grand Slam fell on the Bielefeld Viaduct, it struck the ground near one of the main support pillars. For a moment, nothing seemed to happen. Then the ground erupted. A mushroom cloud of dirt, rock, and debris rose hundreds of feet into the air. When it settled, one entire span of the viaduct had collapsed. The stone arches that had stood for over a century were reduced to rubble. One bomb had accomplished what hundreds of conventional attacks had failed to do. If you're enjoying this deep dive into one of World War II's most fascinating secret weapons, take a moment to help us out by subscribing and hitting the notification bell. These stories take extensive research to bring to you, and your support helps us continue uncovering these incredible historical accounts. Also, share this video with anyone who loves military history and engineering marvels. The destruction of the Bielefeld Viaduct sent shockwaves through German military planning, both literal and figurative. Transportation networks began failing across the country. The Arnsberg Bridge was next, its massive stone piers no match for the seismic hammer of Grand Slam. The Nienburg Bridge followed. Then the Bremen railway bridges. Each strike was surgical, precise, devastating. These weren't area bombing raids that killed thousands of civilians. These were pinpoint strikes against military infrastructure, carried out with unprecedented accuracy and effect. But perhaps the most dramatic demonstration of these weapons came against a target that had become legendary for its invulnerability: the Valentin submarine bunker near Bremen. This was one of the most massive concrete structures ever built, designed to be a bomb-proof factory for constructing U-boats. The main roof was over 14 feet thick, a solid mass of steel-reinforced concrete that the Germans believed could never be penetrated. They were wrong. In March 1945, a raid by Lancasters carrying both Tallboy and Grand Slam bombs struck the bunker. The bombs didn't penetrate the roof directly. They didn't need to. Buried in the ground around the structure, their explosions created shock waves that fractured the concrete from within. Cracks appeared in the massive walls. Sections of the roof began to separate from the support columns. The structure, which had taken thousands of workers' years to build, was rendered useless in a single afternoon. German engineers who inspected the damage were mystified. They examined the crater patterns, the fracture lines in the concrete, the way the structure had failed. None of it matched their understanding of how conventional bombing worked. They found evidence of the bombs having penetrated impossibly deep into the ground before detonating. They measured the seismic damage and couldn't believe what they were seeing. In reports that were later captured by Allied intelligence, German officers described the weapons as unearthly, impossible, like something from sorcery rather than science. They used terms that translated to magic and witchcraft because they simply had no other frame of reference for what they were witnessing. The psychological impact was enormous. German engineers and construction crews who had been confident in their fortifications now lived in fear. Every bunker, every bridge, every tunnel was suddenly vulnerable. The concrete that was supposed to protect them had become unreliable. Morale among U-boat crews plummeted. They knew that their bases could be destroyed at any moment, that the massive concrete shelters were no longer safe. Construction programs for new fortifications were abandoned. What was the point of building walls 20 feet thick if the British could simply shake them apart from below? What made Tallboy and Grand Slam so revolutionary wasn't just their size or explosive power, it was the scientific understanding behind them. Barnes-Wallis had done something that seems obvious in hindsight, but was revolutionary at the time. He had studied how structures actually fail and designed a weapon specifically to exploit those weaknesses. He understood that concrete's compressive strength was impressive, but its tensile strength was limited. He knew that seismic waves could propagate through solid rock and that resonance effects could amplify the damage. He had taken principles from mining, seismology, and structural engineering and combined them into something entirely new. The bombs were also remarkably precise for their era. The streamlined shape and spin stabilization meant they followed predictable trajectories. Skilled bombardiers could place them within yards of their aim point from altitudes of 20,000 feet or more. This was at a time when most bombing raids were considered successful if they hit within a few hundred yards of the target. The accuracy of these weapons meant that crews could attack with surgical precision, destroying specific structures while leaving surrounding areas relatively untouched. Consider the attacks on the Krems Dam on the Rhine River. This barrage controlled water levels that affected German defensive positions and Allied crossing points. It was a small target, well defended, and had to be destroyed without causing catastrophic flooding that would harm civilians downstream. Tallboy was the perfect weapon for the job. On October 7, 1944, 617 Squadron attacked the dam with just 9 aircraft. 5 direct hits were scored. The precision of the strike was remarkable, damaging the sluice gates and rendering the barrage inoperable without causing the mass flooding that conventional area bombing would have risked. The technical challenges of using these weapons can't be overstated. The Lancaster bombers had to be flown to their absolute ceiling, sometimes above 20,000 feet, in unpressurized, unheated aircraft. Crews endured temperatures of 40 degrees below 0 Fahrenheit while wearing oxygen masks. The bombers had to maintain steady, level flight during the final approach to the target, making them vulnerable to anti-aircraft fire. The bombardiers had to calculate wind drift, temperature, barometric pressure, and dozens of other variables to achieve the accuracy required. A single mistake could mean the bomb would miss by hundreds of yards, making it ineffective. And the weapons were expensive. Each Grand Slam cost approximately 14,000 pounds sterling to produce, equivalent to millions of dollars in today's money. Only 41 Grand Slams were ever dropped operationally during the war. Each one had to count. The precision required meant that missions could only be flown in good weather with excellent visibility. Crews sometimes flew hours to reach a target only to find it obscured by clouds and have to bring the precious bomb back to base, a nerve-wracking experience given the weapon's size and the stress it placed on the aircraft. The manufacturing process for these bombs was equally challenging. The steel casings had to be forged and heat-treated to exact specifications. Too soft and they would shatter on impact before penetrating. Too hard and they would be brittle and crack. The tolerances were measured in fractions of millimeters. The explosive filling had to be poured carefully to avoid air pockets that could cause the weapon to detonate prematurely. Each bomb took weeks to produce, and skilled craftsmen were in short supply. Barnes-Wallis personally supervised much of the early production, insisting on quality control standards that seemed excessive to some, but were absolutely necessary for the weapons to function as designed. The targeting information required for these missions was also extraordinarily detailed. Intelligence officers had to know not just where a bridge or bunker was located, but the exact geology of the surrounding area. Was the bedrock solid granite that would transmit shock waves effectively, or was it soft soil that would absorb energy? How deep were the foundations? What was the structure's weak point? Reconnaissance aircraft took thousands of photographs. Agents on the ground provided measurements and diagrams, Engineers studied pre-war architectural plans. Every mission was planned with the precision of a surgical operation. One of the most impressive attacks came on March 19, 1945, against the Arnsberg Railway Viaduct. This massive stone structure carried a critical rail line through the hills of central Germany. It had been attacked more than 50 times by conventional bombers without success. The viaduct was simply too solid, its arches too thick. When 617 Squadron arrived with Grand Slam bombs, they achieved what seemed impossible. The first bomb struck near the base of a central pier and penetrated deep into the hillside. The explosion that followed was visible for miles. When the smoke cleared, 2 entire spans of the viaduct had vanished, leaving a gap nearly 200 feet wide. The structure that had stood for decades was erased in seconds. German railway officials who inspected the damage filed reports expressing disbelief. They documented how the explosion had occurred deep underground, how the stone piers had been lifted bodily off their foundations before disintegrating. They noted that the explosive force seemed to have come from below rather than above. The terminology they used suggested they thought the British had somehow planted mines underground, because the alternative explanation that a bomb had fallen from an aircraft and then penetrated 100 feet into solid rock seemed physically impossible. This was exactly the reaction Barnes-Wallis had hoped for. He understood that a weapon's psychological impact could be as important as its physical effects. The fact that German engineers couldn't comprehend what was happening made the attacks even more demoralizing. It suggested that the British had achieved some technological breakthrough that left German science behind. In reality, it wasn't new technology, but new thinking, applying known principles in innovative ways. But the Germans didn't know that, and their confusion worked in the Allies' favor. As the war entered its final months in early 1945, Tallboy and Grand Slam attacks intensified. The weapons were used against the last remaining U-boat pens, against railway bridges, feeding the increasingly isolated pockets of German resistance, against command bunkers, and against any hardened target that conventional bombing couldn't touch. The psychological effect on German commanders was devastating. They began to realize that there was literally nowhere they could hide, no bunker deep enough or strong enough to provide safety. One particularly significant series of attacks targeted the bridges over the Rhine River as the Allies prepared to cross into the heart of Germany. These bridges were Germany's last line of defense. If they could be held and kept intact, German forces could retreat across them and then destroy them to slow the Allied advance. But if the Allies could destroy the bridges while German forces were still on the wrong side, thousands of troops would be cut off. Tallboy and Grand Slam made the difference. Bridge after bridge fell to these weapons. The Nienburg Railway Bridge, a massive steel and stone structure, was destroyed with 3 direct hits. The Bremen bridges were collapsed. The Arnsberg Viaduct was reduced to rubble. The most dramatic bridge attack came at Bielefeld, which had been struck before, but required multiple missions to completely neutralize. On March 14, 1945, a force of Lancaster bombers arrived carrying both Tallboy and Grand Slam bombs. The viaduct was defended by heavy anti-aircraft batteries and fighters, but the Lancaster crews pressed their attack. One Grand Slam struck directly beside a main support pier. The explosion was so violent that it was recorded by seismographs over 100 miles away. When the dust settled, over 100 yards of the viaduct had simply ceased to exist. It was the final nail in the coffin of Germany's transportation network in that region. The effectiveness of these weapons raises an interesting question. Why weren't they developed and used earlier in the war? The answer lies in the complex relationship between innovation and institutional resistance. When Wallace first proposed his deep penetration bomb concepts in 1941, he was met with skepticism from many quarters. The Air Ministry was focused on area bombing campaigns against German cities, not precision strikes against individual targets. Resources were stretched thin, and investing in experimental weapons seemed risky when conventional methods were producing results, however inefficient. It took the persistent failures against hardened targets to change minds. The inability to destroy U-boat pens was costing merchant ships and sailors' lives in the Atlantic. The failure to destroy key bridges was allowing German forces to move troops and supplies. Eventually, the military establishment recognized that some targets simply couldn't be destroyed with conventional methods, no matter how many bombers were sent or how many tons of explosives were dropped. That's when Wallace's ideas finally received the support they needed. There's also the matter of manufacturing capacity and bomber availability. In 1941 and 1942, Britain was barely surviving, producing just enough bombers and bombs to maintain the air campaign. It wasn't until 1943 and 1944, when British and American production reached full capacity, that resources could be spared for specialized weapons. The modified Lancasters required to carry Grand Slam weren't available until late 1944. Even Tallboy required modifications that took time to implement across the bomber fleet. The story of these weapons is also a reminder of the importance of individual genius in warfare. Barnes Wallis was not a military man. He was an engineer who happened to be brilliant at applying scientific principles to practical problems. His willingness to question conventional wisdom and think in terms of physics rather than tradition made all the difference. The military establishment deserves credit for eventually recognizing his brilliance and giving him the resources to prove his concepts, but it was Wallace's vision that made it all possible. After the war, when Allied intelligence teams interviewed captured German engineers and officers, the extent of the psychological impact became clear. Many German technical experts admitted that they had been completely mystified by the effects of Tallboy and Grand Slam. They had examined the damage patterns, studied the crater formations, and measured the seismic effects, but they couldn't reverse engineer the British methods. Some thought the bombs must have had some special explosive more powerful than anything Germany had developed. Others speculated about guidance systems or delay fuses. Very few correctly identified the key, the combination of weight, velocity, and penetration depth that allowed the explosion to occur at precisely the right location to maximize structural damage. The term that kept appearing in German reports, translated variously as witchcraft, sorcery, or black magic, wasn't used literally, of course. These were educated engineers, not superstitious peasants. But the terminology reflected their genuine bewilderment. They were seeing effects that their understanding of physics and engineering said shouldn't be possible. Massive concrete structures that should have been invulnerable were crumbling. Bridges built to last centuries were collapsing after single bomb hits, and they couldn't figure out how the British were doing it. In the absence of a rational explanation, the metaphor of sorcery seemed appropriate. It's worth noting that Germany actually had some scientists who understood similar principles. German engineers had experimented with penetration weapons for use against French fortifications before the war, but they never pursued the concept with the same rigor and resources that Britain devoted to it. Partly this was because Germany's early war successes made such weapons seem unnecessary. When your blitzkrieg tactics are sweeping across Europe, why invest in expensive specialty bombs for attacking fortifications? By the time the Germans were on the defensive and could have used such weapons themselves, they lacked the resources and industrial capacity to develop them. The post-war analysis of Tallboy and Grand Slam attacks revealed just how effective they had been. Intelligence assessments estimated that these specialized weapons, representing less than 1% of the total bomb tonnage dropped by the RAF, had destroyed or heavily damaged more high-value strategic targets than the rest of the bombing campaign combined. Dozens of bridges, viaducts, U-boat pens, and bunkers that had survived hundreds of conventional attacks were neutralized by one or two precision strikes with earthquake bombs. The cost-effectiveness was staggering. This has implications for modern military thinking. The precision-guided munitions of today, cruise missiles and smart bombs that can strike within meters of their target, are the direct descendants of the concepts Barnes-Wallis pioneered. The idea that one precisely delivered weapon can be more effective than hundreds of conventional ones has become fundamental to contemporary warfare. Modern bunker-buster bombs use similar principles to Tallboy and Grand Slam, relying on penetration depth and precise placement rather than sheer explosive power. The legacy of these weapons extends beyond their immediate military impact. They represented a fundamental shift in how engineers thought about solving problems. Instead of just making bombs bigger, Wallis asked how to make them smarter. He studied the target's vulnerabilities and designed a weapon to exploit them. This methodology, combining physics, materials science, and systems thinking, became a model for weapons development throughout the Cold War and beyond. The men who flew these missions deserve recognition as well. The crews of 617 Squadron and other units equipped with these weapons were among the most skilled in the RAF. They flew some of the most dangerous missions of the war, attacking heavily defended targets with expensive, irreplaceable bombs that had to be placed with pinpoint accuracy. The casualty rates for these elite units were significant, but they never wavered. They understood they were wielding weapons that could shorten the war and save lives by destroying targets that conventional bombing couldn't touch. Wing Commander Leonard Cheshire, who pioneered many of the tactics used to deliver these weapons, was awarded the Victoria Cross, Britain's highest military honor. After the war, he devoted his life to humanitarian work, founding homes for people with disabilities. But he always spoke with pride about the precision bombing campaigns, arguing that they were more humane than area bombing because they reduced civilian casualties while increasing military effectiveness. Barnes-Wallis himself continued to innovate after the war. He worked on supersonic aircraft design, variable geometry wings, and various other advanced aerospace concepts. He was knighted in 1968 and received numerous honors for his contributions to engineering. But he always considered the earthquake bombs among his most important achievements, not just for their military success, but because they demonstrated the power of scientific thinking applied to practical problems. In the final weeks of the war in Europe, as Allied forces closed in on Berlin from all sides, Tallboy and Grand Slam continued to strike. The last V-2 rocket storage facilities in the Netherlands were collapsed. The remaining submarine pens were sealed. Railway bridges that could have allowed German forces to regroup were destroyed. Each mission brought the end of the war closer. By the time Germany surrendered in May 1945, there were few hardened targets left standing. The concrete fortresses that had seemed invincible at the start of the war had been reduced to rubble by weapons that seemed like magic. The story of the shell that split concrete bridges like butter is ultimately a story about the power of innovation in warfare. It's about how one brilliant engineer, thinking outside the conventional wisdom, developed a weapon that changed the strategic picture. It's about how the application of scientific principles could achieve what brute force could not. And it's about how the most effective weapons aren't always the biggest or most powerful, but the ones designed with the deepest understanding of how to exploit an enemy's weaknesses. The Germans who called these weapons witchcraft weren't entirely wrong in spirit, even if they were incorrect in fact. What Wallis had achieved did seem almost magical. The ability to destroy seemingly indestructible structures with single bombs, to create earthquakes on command, to make massive bridges and bunkers crumble as if made of sand. But it wasn't magic. It was science, engineering, and brilliant thinking applied to the oldest problem in warfare: how to destroy what your enemy has built to protect himself. Today, few people outside of military history enthusiasts have heard of Tallboy and Grand Slam. They lack the fame of other World War II weapons like the atomic bomb or the V-2 rocket, but in their own way, they were just as revolutionary, just as significant. They proved that precision could trump power, that understanding your target was more important than overwhelming it, and that innovation could come from unlikely places. Barnes-Wallis wasn't a general or an admiral, he was an engineer with a slide rule and a deep understanding of physics. And with those tools, he created weapons that seemed impossible, weapons that his enemies literally couldn't believe existed. The concrete bunkers and bridges of Nazi Germany stood as symbols of their military might, testament to engineering prowess and industrial power. They were meant to be permanent, unbreakable, invincible. But they all fell, shaken apart by seismic shock waves from deep underground, destroyed by weapons that exploited the fundamental physics of how materials fail under stress. To those who didn't understand the science, it must indeed have seemed like witchcraft, like some dark power that could make solid concrete flow like water and massive stone arches crumble like old bread. But it was something far more powerful than magic. It was human ingenuity applied to the problem of war, and it helped bring one of history's darkest conflicts to a close. Before we close, if this story fascinated you as much as it did us in researching it, please consider sharing this video with other history enthusiasts. Leave a comment telling us what aspect of World War II engineering and innovation you'd like us to explore next. Your engagement helps us continue bringing these incredible untold stories to light. Thank you for watching.